Now moving onwards, we are going to start the three famous equations: conservation of mass equation, conservation of momentum equation, and conservation of energy equation. So over here, let's consider that the fluid is flowing over a surface, over a plate, and this within this fluid we have this differential element having dimensions dx and dy in y and z respectively. The free stream velocity of the fluid is u infinity, and the free stream temperature of the fluid is T infinity. And this element has a unit depth in z direction. Now starting with the conservation of mass equation, over here that is the same element, that is the same differential element that we were looking at on the last page, which has got the dimensions of dx and dy. Over here we have this the velocity in the x direction as u, and when the fluid would come out of this differential element, its velocity would then become u plus dou u by dou x times dx. This is the same thing that we have been discussing, that we have already discussed for a number of times, and we had discussed it in chapter number 2 while deriving heat diffusion equation for the very first time, where of course it was not the velocity but the temperature, but the application is the same for the Taylor's expansion. And similarly, v is the component of the velocity in y direction, and the incoming velocity into this differential element is v, and the velocity with which the fluid will come out of this differential element would be v plus change in velocity with respect to y, means dou v by dou y times the total length in y direction, which is dy. So conservation of mass equation would be written in this form, where the rate of mass flow into the control volume would be the same as the mass flow rate coming out of the control volume. Now the mass flow rate which is coming into the control volume is in two dimensions, one along y-axis, one along x-axis, and the other one along y-axis. So the rate at which the fluid enters the control volume from the left surface, it enters from the left surface and it enters from the bottom surface. So these two are the fluid, the flows which are coming into the control volume, and the right and the top are the two faces from which the fluid is leaving the control volume. So that may very simply be written as density area times velocity, because mass flow rate as per continuity equation may be written as density area velocity. So density is rho, and then the area which will be in the way of u would be dy, this length times the length in z direction, which is 1, and the velocity component in x direction is u. Similarly, the rate at which the fluid would leave the control volume from the right surface would again be density area velocity. Density would remain the same, the area would also remain the same, however u would be written in this form as just discussed. Similarly, the rate at which the fluid enters the control volume from the bottom is again density area velocity, where density would remain rho, and the area through which this fluid is entering the control volume would be dx, this length, times the length in x times the length in z direction, which is 1, times the velocity, which is v. And similarly, the rate at which this fluid will leave the control volume from the top surface would again be density times area times velocity, where the velocity would be written in this form, indicating the change in y direction. Now the rate of the mass flow into the control volume, so we have to add these two, we have to add this one, and this one. We have to add these two, and these two will appear over here on the left hand side of the equation. And this is the mass flow leaving the control volume, and this is also the mass flow which is leaving the control volume. So these terms would appear on the right hand side of the equation over here. And then various terms would get cancelled out. For example, rho dy times u will get cancelled out by rho dy times u on the right hand side. Similarly, rho dx times v on the left hand side will also get cancelled by this rho dx times v on the right hand side. So we would be left with two terms only, rho dy times 1 times dou u by dou x dx, which is written over here, plus rho dx times 1 times dou v by dou y times dy, which is written over here. Now dividing throughout by the volume means dx, dy and 1, we will be left with dou u by dou x plus dou v by dou y as 0. So this equation is called as conservation of mass equation. Now moving further, we then have the conservation of momentum equation. Conservation of momentum equation is based upon the Newton's second law, which says that the product of mass into and acceleration is the net force move in that particular direction. So over here we would write the mass as delta m, where delta m is the mass of the differential element that we were looking at, which has got the dimensions of dx and dy. And then acceleration in x direction is written as ax, would be equal to the net force. And in here there are two types of forces, the surface force and the body force. Surface forces are those forces such as the frictional force or the pressure, whereas the body force is in fact the weight. So now writing this mass as a product of density and volume, because by definition density is mass per unit volume, so therefore mass would be density times volume. So in place of delta m we may write rho means density times the volume of this differential element, which is dx times dy times 1. And in order to have area in x direction, kindly note that we would be using this expression to get the expression for acceleration. So acceleration would be the derivative of the velocity. Now in order to get the derivative of velocity, in order to differentiate u, we must have the expression for u. So since the flow is two-dimensional, u is a function of x and y, so therefore the total differential of u would be dou u by dou x times dx plus dou u by dou y times dy. So change in the velocity in x direction times dx plus change of that component in y direction times the total length in y direction, which is dy. So now if we differentiate this thing with respect to t, so what we will get? It would be dou u by dou x, and then this may be written as dx over dt. And similarly the second term would be dou u by dou y times dy by dt. Now dx by dt is in fact change in distance per unit time, or change in displacement per unit time, so that would be the velocity. And similarly this would also be the velocity, displacement per unit time. So dx by dt would be written as u, because it is the change in the displacement and distance in x direction, whereas dy by dt for the same reason would be written as v. So this is A. So what we will do is that we will now put this mass in here, and we will put this expression for acceleration in here as well, along with the surface forces on the right hand side. So considering the surface forces, before we write the acceleration and mass over there in F is equal to ma. Over here we are being shown the two types of forces. One is the stress force and the other one is pressure. And as you already know that pressure always acts on the surface, on the body. So therefore the arrows have got the this particular invert direction, or onto the they have the direction onto the control volume, differential control volume. So if we take care of all the surface forces, so in fact you can see over here that we are considering the two surface forces as I was explaining on the previous slide, means the shear stresses and the pressure. So the difference of these two means the difference of the shear stresses. Again over here it is tau, and over here it would be tau by tau y times dy. So it has been written in the same form as we have written the velocity while deriving the conservation of mass equation, and in the same manner that we had written change in temperature while deriving the heat diffusion equation. So the same form of Taylor's expansion has been made use of, or you may simply call it a unitary method. So the difference of tau and this thing would give us tau by tau y times dy. So it has been written over here, and since it is shear stress and we are talking about the force on the left hand side, so this shear stress needs to be multiplied with the area so as to get the force. So the area that this shear stress is incident upon is acting upon would be dx times 1, dx times 1, and then the difference of this p and this p would give us tau p by tau x times dx, but with a negative sign. Of course you can see p would get cancelled out, and tau p by tau x times dx would be acting in this particular direction, means negative x direction. So it would be written with a negative sign, and again this p needs to be multiplied with the area that it is acting upon, and that so as to get the force. So therefore this p is acting upon dy times 1, so it will be multiplied with dy times 1. So we can see over here dx times dy times 1, and over here we have dx times dy times 1. So we can take dx times dy times 1, which is the volume of this differential element, common out of both these terms. So we would be left with tau by tau y minus tau p by tau x. And then using that particular equation which you had for the first time, probably for the first time seen in the fluid mechanics course, and this is the same expression that we also had discussed in the initial slides of this particular chapter, where tau was mu times tau u by tau y. So therefore tau by tau y would be the second derivative of velocity with y, where mu would remain mu minus tau p by tau x times the volume. Now we will put the expression of mass, the expression of acceleration, and the expression of surface forces in this particular equation, which we had seen a couple of slides back. So mass would be written as density, product of density and volume, and area, acceleration ax is being written in this form, which we had sort of derived on the last page, and the surface forces are written in this form. We are not considering body forces because there would not be considerable changes in the body forces. There would not be considerable changes in the weight. Now on both sides we can see that this volume exists on both sides of the equation, so it will get cancelled out. Dx times dy times 1 will get cancelled out from both sides of the equation, and therefore on the left hand side we would have a rho times this expression for acceleration, and on the right hand side we would have mu times second derivative of u with y minus tau p by tau x. Now we are going to consider three very easy but in fact very important points, and those points are called boundary layer approximations. So in boundary layer approximation, these are a few points that we would be discussing. The first one says that in a boundary layer, the velocity component in the flow direction is much larger than it is in the normal direction. The velocity component in the flow direction, means along x direction, is much larger than it is in the y direction. Thus u is much greater than v, and therefore dava v by dava x and dava v by dava y are negligible, since u is much greater than v. Because if you take a look, this is the flow direction, and the component of velocity in x direction is u, and the component of velocity in y direction is small v. So since u is much greater than v, of course, because majorly the flow is taking place in x direction, so therefore u would certainly be much greater than v. Therefore since v is itself very small, so therefore change of v in x direction and change of v in y direction would be negligibly small. That is the first point of discussion. The second is that also u varies greatly with y in the normal direction, from 0 at the wall surface to nearly the free stream value across the relatively thin boundary layer. So if you take a look over here, if you take a look at the velocity profile, so due to the no slip condition, the velocity over here, if the plate is at rest, so therefore the velocity of the very first layer of fluid which is in direct contact with the surface would also be 0, and we have discussed no slip condition previously. So therefore the velocity over here at this point would be 0, and then as we move away from the plate, the velocity would keep on increasing. The velocities would keep on increasing because the effects of the plate would get smaller and smaller and smaller. So the velocities of the subsequent layers of fluids would be greater than 0. Let's say 0.5, 1, 1.5, 2, 2.5 meters per second, and so on. And there would come a point where the velocity would approximately be the same as u infinity, and that would be the end of the boundary layer. And we have seen that if the velocity is approximately 99% of u infinity, so that is the thickness of the boundary layer, and after which the velocity would be 100% of u infinity. So u varies greatly in the velocity varies greatly in y direction. The velocity varies greatly in y direction, and this is what is written over here. U varies greatly in with y in the normal direction, means in the y direction, from having a value of 0 at the wall surface, at the liquid, at the fluid and surface interface, to nearly the free stream value, to nearly approximately u infinity across the boundary layer, while the variation of u along with x, means along with the flow, is typically small, because if the fluid is flowing at, let's say, 5 meters per second, so it will keep on moving with 5 meters per second. I am talking about x direction, but due to the development of the boundary layer, the u will vary greatly within the boundary layer from a value of 0 to the value of u infinity at the end of the boundary layer. So in fact u is varying in y much more as compared to the variation of u in x. Therefore dava u by dava y would be much greater than dava u by dava x. Now similarly, if the fluid and the wall are at different temperatures and the heat transfer is taking place between the fluid and the surface, and if the fluid is heated or cooled, it may be either case. If the fluid is at lower temperature, it would get heated up, or vice versa. So the heat conduction will occur primarily in the direction normal to the surface, and thus, okay, let's discuss this thing over here as well. We can see that the temperatures would vary over here. We can see that the temperatures would vary in y direction as we move away from the plate, just like the velocity was varying majorly in y direction as we were moving away from the plate. So therefore the temperature will also change majorly in y direction as we move away from the plate. So therefore change of temperature in y direction would be greater than the change of temperature in x direction. This is what is written over here in the third point. If the fluid and the wall are at different temperatures and the fluid is heated or cooled during the flow, heat conduction will occur primarily in the direction normal to the surface. So the heat transfer would occur primarily in the direction normal to the surface, means over here in y direction, and thus dou t by dou y would be much greater than dou t by dou x. So the velocity and temperature gradients normal to the surface would be much greater than those along the surface, means dou t by dou y and dou u by dou y would be much greater than their counterparts in x direction. These simplifications which we have discussed over here are called boundary layer approximations. So those are called boundary layer approximations, and they simplify the analysis with a little loss in accuracy. Now moving on with the conservation of the momentum equation. So we have put the expressions for mass by writing it in the form of density times volume, the expression for acceleration, and the surface forces in x direction. Now we are going to do the same in y direction. So delta m means a small elemental mass of the differential element times the acceleration in y direction would be equal to the surface forces in y direction and body forces in y direction. Again, as described, we did not consider the body force over there while we were writing this expression for x direction, because the weight will not vary within the boundary layer due to a very small change in height. Now we will be doing the same thing over here, means we will write ay as dv over dt, just like we had written ax as du by dt. So dv would be written in this form again. Again, v is a function of x and y because the flow is two-dimensional. So therefore dv would be written as dou v by dou x times dx plus dou v by dou y times dy. And if we divide this whole expression by dt so as to write acceleration in y direction, this would be dx by dt and this would be dy by dt. However, acceleration in y direction would be negligibly small, right? So it would be negligibly small because we have seen on the previous page that dou v by dou x and dou v by dou y are negligible. This was the first point that we had discussed over here, that dou v by dou x and dou v by dou y are negligible. So therefore dou v by dou x and dou v by dou y are both negligible. So therefore their product with any of the terms would also be negligibly small, and therefore dou p by dou y would become 0. Now dou p by dou y would become 0, and why it would become 0? Because if we take a look over here, so over here ay is negligible. So ay is negligible. This is what we can see from here, that ay is negligible. So the right hand side would be approximately 0. and while considering the surface forces, because we are not considering the body forces, so while considering the surface forces, in the case of surface forces, it would be only the pressure, right? Dou P by dou Y on the right hand side of the equation, as we had written for the surface forces in x direction. Yes, we had written there were two terms on the right hand side while we were writing the surface forces in x direction. So therefore dou P by dou Y would therefore become equal to 0. So that would mean that the variation of pressure in the direction normal to the surface is negligible, and therefore the total change would be in x direction. Of course, dou P by dou Y, if it is 0, then that would mean that the change in pressure in y direction means that the variation of pressure in the direction normal to the surface, means in y direction, is negligible, and thus the total change in pressure would be in x direction. Therefore dou P by dou x can then be written as dP by dx, because dou P by dou y is 0, as discussed over here. Just one last line which was written over here at the bottom. It follows that for a given x, the pressure in the boundary layer, inside the boundary layer, would be the same as the pressure which is in the free stream. Why? Because if pressure is not changing in y, if the pressure is not changing in y, as is written over here, the dou P by dou y is 0, it means that if we move in y direction, the pressure will not change. So if we move in y direction and the pressure is not changing, it means that the pressure inside the boundary layer would be the same as the pressure outside the boundary layer. And what is the pressure outside the boundary layer? It is the pressure of the free stream fluid. So therefore pressure within the inside the boundary layer would be the same as the free stream pressure. Now over here it says that the velocity component in the free stream region. So we are now talking about the region outside the boundary layer, free stream region. So over there the velocity is constant. We usually represent it with u infinity is constant, and v is in fact 0, because there is no y component of velocity outside the boundary layer in the free stream region, because it would be flowing all along x-axis. So therefore this equation which we had derived a little bit earlier, I will show you. This is the same equation that we had written over here. Rho times u dou u by dou x plus v times dou u by dou y is mu times second derivative of u with y minus dou p by dou x. So this is the equation that has been written over there. Now this equation, in this equation u is constant, so dou u by dou x would be 0, and v is 0, right? So both the terms on the left hand side would become 0, and since u is constant, its derivative with y would be 0. So therefore dou p by dou x would become 0 in the free stream region. So therefore for the flow over flat plate, the pressure remains constant over the entire plate, because dou p by dou x is 0. It means pressure does not change with x, and we have just discussed that over here we have just discussed that the pressure inside the boundary layer at any given x, the pressure inside the boundary layer is equal to the pressure in the free stream. So at any x along the length of the plate, at any particular location, at any particular x, the pressure within the boundary layer would be the same as the free stream pressure. And over here we are discussing that the pressure does not change in the flow direction. The pressure does not change in the flow direction because of those things that we have just discussed, that u is constant, so therefore dou u by dou x would become 0, and v is itself 0 in the free stream region. So therefore the left hand side would be 0, and u does not change in y because we are outside the boundary layer, we are not inside the boundary layer, so u will not change in y direction. So therefore its derivative will also be 0, and therefore dava p by dava x would become 0. So it means that pressure does not change in x direction. It means that pressure remains the same in the flow direction over the entire plate, Now moving on to the third equation, which is called the conservation of energy equation. So over here I would explain it a little bit, and then I will leave it to you. There are three types of, first of all, energy conservation of energy equation says that the total energy change in the energy content of a system would be 0. Means energy in would be equal to energy out in a system, or E in minus E out would therefore be 0 if the total change in the energy of the system is to be 0. Now over here there are three types of energies that we are considering. One is delta E due to heat, the other one is delta E due to work, and the third one is delta E due to mass. So for the change in the total energy of the of this differential element, we are writing it as mass flow times E stream, where E stream is the total energy of the stream in x direction. So this is E in minus E out due to mass in x direction. Similarly, we have E in minus E out due to mass in y direction. So it would be this quantity minus again the same thing which we have written previously for temperature, for velocity, and for u and v as well, right? So it would be mass flow times E. So we will take its derivative in x direction, and then we will multiply it by the total length in x direction, which is dx. So of course these two terms will get cancelled out. These two terms will get cancelled out, and we will be left with this term only. So it would be dava by dava x of m dot times E times dx, and then we can write this mass flow rate as density, as a product of density, area, and velocity. So we have written it in the form of density times area. Area would therefore be dy into 1 if you are talking about x direction, and times velocity in x direction is u, and the total energy can be written as cpt, right? So over here it would be dava, so this the things which are constant, such as density, such as the volume, means dy into 1 times dx would become the volume, and then cp will also be taken out of the differential sign. So it would be dava by dava x of u into t. It would be dava by dava x of u and t. Again cp is a constant, so therefore it will also be taken out of the differential sign. So it would be first variable means u times the derivative of second, means dava t by dava x, plus the second variable means t times the differential of the first variable, means dava u by dava x. Right? So this would be the E in minus E out in due to mass in x direction. Similarly, we can write the E in minus E out total change in the energy delta E due to mass in y direction as similarly we can write it in this form, right? So it would be minus rho Cp, it would remain minus rho Cp times the volume dx dy into 1, and then instead of u we will write v, instead of dava t by dava x we will write dava t by dava y, and similarly over here in place of dava u by dava x we will write dava t by dava y, right? So if we then add the two, we will end up with this equation where we would have minus rho Cp times volume, and then if we add these two, so therefore see, we have u dava t by dava x over here, we have u dava t by dava x over here, and we have v dava t by dava y over here. We have v dava t by dava y over here. We do not have this term. We do not have this term over here in the last expression, and we do not have this term over in the last expression. The reason is that when we will take t common out of these two terms, we would have dava u by dava x plus dava v by dava y. We would have dava u by dava x plus dava v by dava y if we take temperature common out of these two terms, out of these two terms. So as per the conservation of mass equation, dava u by dava x plus dava v by dava y is 0. So using that particular equation, that would become 0, and we would be left with this term only. We would not be considering the delta E due to the work for the obvious reason that we are considering heat and mass transfer only. So due to heat, it would again be Qx minus Q plus dava Q by dava x times dx, and over here we know that this Qx and this Qx will get cancelled out, so it would be minus dava Qx by dava x times dx. And again it is dava by dava x of qx, so dava by dava x of qx, so qx can be written as minus ka dava t by dava x, and dx is written as it appears. So this minus and minus sign would become plus, k would be taken out of the differential sign, and dy into 1 will also be taken out of the differential sign, upon which upon multiplication with dx would become the volume, and within the bracket we would have second derivative of t with x. Similarly, in the y direction, we can write it as k times volume times second derivative of temperature in y. So if you then add these two, if you then add the delta T due to heat in x in x and y, so k times volume would be taken out as common, and we would have second derivative of T with x plus second derivative of T with y, right? So if we then put it in that conservation of energy equation, we will end up getting this equation in the last. So that was about the derivation of the conservation of mass, conservation of momentum, and conservation of energy equations. We have also discussed the changes of velocity u and v within the boundary layer and outside the boundary layer. We also have discussed the change in pressure at any particular x within the boundary layer and outside the boundary layer, and we have also discussed that the pressure does not change if in the flow direction, and we have also discussed boundary layer approximations as well. So that was all about these three equations and the boundary layer approximations.